H, specific heat at constant pressure. Let's review a little from the previous chapter. The heat capacity is defined as big C, taking the limit as delta T, temperature goes to 0, of heat put into a substance and dividing by the change in temperature. And this Q, it would be nice if we could have a delta there so we could get a real derivative. So what I'm going to do is a quick review of what we did the last class. We said that the first law of thermodynamics says that the change in the energy is the heat put into the system minus the work done, and the work done is the pressure times the change of volume. When the gas expands, it loses energy. So that's why we have the minus sign there. So that means that Q is equal to delta U plus the W, which is plus P delta V. So then we come over here and we can then take the limit here of delta T going to 0. And for the Q, we put these in. We have delta U plus P delta V all over delta T. So that means the heat capacity can be written as two terms. First term is delta U over delta T in the limit as delta T goes to 0. And the second term is P times the limit delta T goes to 0 of delta V over delta T. And now we have two good derivatives. So we could then write C as the derivative of the energy with respect to the temperature plus pressure times the derivative of the volume with respect to the temperature. So this is the equation I mentioned I would be starting with this class with, but we did a quick review of deriving it. And we have looked at in our course ideal gas law for monatomic gases, one atom. Then you have point particles, 1/2 m naught V squared average, and this is the mass of the particle, is equal to 3/2 kT, where kT is the Boltzmann constant. We derived that before. And if you want the energy of the gas, you would multiply by the number of particles. Number of particles times 1/2 m naught, the mass of a gas particle, times the average velocity squared. See, this is the kinetic energy. So the kinetic energy of the gas is related to 3/2 kT. So here we can write this as then 3/2 n kT. Now remember, this n is the number of particles. And when we go to chemistry and we want to deal with the number of moles, little n, then we have a new gas constant, which is the ideal gas constant, and we call that R star in our class because we reserve R. You might remember that R is equal to R star over the molar mass of the gas. And this dates back to our equation 3. We're deriving about 30 equations in this course leading up to our big derivation of the adiabatic Lapse rate. So just to keep that in mind, that n times k, where n is number of particles and k is the Boltzmann constant, is equal to the number of moles times the ideal gas constant. Now I'd like to show you another relationship. This equation says that R star equals m times R. So I want to put that in there for the R star, and then I would get 3/2 N times MR. And then I have a T there. But see, this is the molar mass, and this is the number of moles. Now, the molar mass is the mass of 1 mole, and the number of moles times that molar mass is the mass of the gas. So that's nice to know also. So what we're saying here is we can write down the energy for our gas as 3/2 N R star T. That's just copying down this one. But then I want to write down 3/2 M RT as an equivalent expression. 3/2 M RT. So you can think this is chemistry and this is atmospheric science. And we'll just say chemistry and atmospheric science. And also physics. I believe we used this when we were in physics, but we threw the star away because we don't deal with R. The R means the ideal gas constant, but for atmospheric science classes, R star is the ideal gas constant, and this R is R star over M, which is called the gas constant, and that depends on the gas. So now we're ready to review last class where we had the heat capacity at constant volume. And constant volume means the derivative of the volume with respect to the temperature is 0, it's gone. So you just have du dt, and we just go ahead and take that derivative again since it's quite easy to do. We just have the expression here. We would simply take the derivative of this expression, we would get the 3/2 N R star. And if we come over here and take the derivative, we would get the 3/2 times MR. And then we can very easily see how we can get the specific heat. The specific heat you divide by the mass in atmospheric science, and in chemistry you divide by the moles. So to make sure we get that right, let me just put a little c and a constant volume and comma n, which means I'm divided by the number of moles. And that's going to be 3/2 R star. Then if I don't put the comma n, I mean divide by the mass. So divided by the mass, you would get 3/2 R. Now we did this already in the last class. This is just a quick review of the last class. Now for the constant pressure, we then go back to our general equation here, and we want du dt. Now, since the u doesn't depend on the pressure, it's the same du dt we have over here, and it's also the heat capacity at constant volume. And then I have to add, though, the plus P dV dt. And now, here I remind myself that this is a constant pressure. So I could put like a little line here, or you can do a bracket and just put a little like a footnote there, a subscript, say P, and that means keep the pressure constant. I don't have to worry about keeping the pressure constant there because the energy doesn't depend on the pressure. Just take the derivative. So this is plus P dV dt at constant pressure. Just go ahead and write that again. There we go. So this is what we want to deal with today. Well, we're going to deal with the ideal gas. So for the ideal gas, remember the ideal gas law is pressure times the volume is the number of moles times the ideal gas constant, R star, times T. So I'm going to just differentiate this. d dt of PV is equal to, well, this is going to be easy because that's just going to simply be, well, I'll write it out. It's d dt of N R star T, but since these are constants, this is just going to give you N R star. And this one, if we use the product rule, we'll get the first times the derivative of the second plus the second times the derivative of the first. And that's n r star. Now we're interested in a constant P. So if you want constant pressure, the constant P is going to imply that this one here is 0. Or that one's gone. So we then have P dv dt. And if we want to emphasize that, we can put down constant pressure like that. There's nothing wrong with doing that. So dv dt at constant pressure, just to remind us, that's equal to n r star. Okay, then we could put that in up here, and we get a very, very beautiful result that this heat capacity at constant pressure is the heat capacity at constant volume plus n r star. Now, at this point, I like to emphasize nr star is mr. So let me emphasize that the number of moles times r star is equal to the mass times r. Helps me go from chemistry to atmospheric science easily. So that means here I can write down Cp is Cv plus, since nr star is mr, I can write this as also mr. Now I can very easily get the specific heats where I divide by the number of moles for chemistry and I divide by the mass for atmospheric science. So little Cp, and I'm going to emphasize that that's moles, put an N there. You take the Cp, the big Cp, and divide by N. So if we do that, we'll have the big Cv divided by N plus R star. But the big Cv divided by N is the little Cv when we're looking at moles, the specific heat, the molar specific heat. Now, if I want to have here the specific heat at constant pressure, where I'm dividing by the mass, I don't have any comma n's for that. I just have the little p, c, little c and a little p. And that's going to equal, if I divide this big C by the M and divide this by the M, I get R. And then this here is little v. So I have this cool relationship that the specific heat at constant pressure is a specific heat at constant volume plus R. Or if we want to use the language of chemistry, we would say that the specific heat, the molar specific heat at constant pressure is the molar specific heat at constant volume plus the ideal gas constant, the R star. So there you have the two. Chemistry here and atmospheric science there. Okay, I thought it'd be nice to see a visualization to go with our equations. Now here's our first law of thermodynamics. The heat transfer is the change in the internal energy of the gas plus P dV, delta V. So you can think of the heat as going into two places. Now, when you have constant volume, this piece is gone. That piece is gone. And we did the derivation in class and show that we had for the heat capacity just the du dt, and that gave us the heat capacity constant volume. Then when you divide by the mass, you get the little c, and here that m goes away. But when you look at constant pressure, you see now the gas has to expand to have constant pressure, because you heat this up, you're going to increase the pressure. It's clamped shut, and everything is going to be in delta U because you can't change the volume. Over here, we let the volume change, so the pressure stays constant. So in that case, you have two pieces. You have the CV we had from before plus the P delta V, at constant pressure, which we showed to be mR. And when you divide by the m, then you get this nice, cute relationship. So just think of the specific heat at constant volume. The heat transfer goes into the internal energy of the gas and the pressure goes up. When you have constant pressure, then the gas expands and the heat is going to be absorbed by the internal energy plus expended with the expansion of the gas doing work. And that allows for the heat capacity to be greater at constant pressure, and the specific heat capacity at constant pressure, once again, is greater than the specific heat capacity at constant volume. And this picture helps us visualize it. I would just like to remind you that we did, in another chapter, we did look at other degrees of freedom where you had a diatomic molecule, and the diatomic molecule could do rotation, and it also had like a spring where it could actually vibrate. And we said that in general, we would take this 3 here and make it an F for the degrees of freedom. So keep that in the back of your mind, that I'm doing this class basically for the monatomic gas, point particles, but you can generalize to the diatomic molecule and molecules in 3 dimensions that have all kinds of ways of absorbing energy by letting the F be the degrees of freedom. In the last class we saw for a diatomic molecule, when the temperature gets higher and higher, you pick up 2 rotational degrees of freedom, a way to absorb energy, and you get a vibrational mode, which has kinetic energy and potential energy. Then we had a 1/2 R star or 1/2 R for each of those degrees of freedom. So general formula, F over 2 and R star T, and the other form you could have it with the MR, but just leave it like this, so that for each degree of freedom you pick up a 1/2 and R star T. Okay, so what we're going to do for the last part of our class today is we want to go back to an equation I derived earlier, which was equation 13, which states that the enthalpy is, this is the specific enthalpy, that's per unit mass, is equal to the energy per unit mass. We use little letters, lowercase, for per unit mass, and that's plus P times the volume per unit mass. And I want to emphasize that the energy is a function of temperature, as we have seen before. So you can think of the equation that we had for 15. This was equation 13, but we had equation 15 in the last class, where we looked at the specific heat at constant volume is d little u dt. So you can integrate this and find that u is CV here, and we'll pretend that's a constant for now in the simple cases, CV T plus a constant, and we can choose the constant to be 0 since energy, you have your choice, and when you have like potential energy, you have energy in general as a reference, you can let that go. So this is just another way of seeing a relationship we already know. We already have seen this before. But I want to do an analogy with the enthalpy, because with the enthalpy here, we can write the enthalpy then, watch this, as CV T plus P alpha. And then equation 2 in our class, we can write the ideal gas law as P alpha is RT. So doing that, we get H is CVT plus RT. But wait a minute, we already have shown that the specific heat at constant pressure is equal to the specific heat at constant volume plus R, using atmospheric science terminology. So if that's the case, look at this. That's just taking the derivative. This is taking the derivative of H with respect to T. The derivative of H with respect to T, you pull off the CV, you pull off the R. So that brings us to our equation 16, where the specific heat at constant pressure, which can also be written as the infinitesimal heat pumped in at constant pressure. You see the infinitesimal change of temperature. You know, I really don't like this because it's like a broken derivative. And this is why we're doing this, because look at this. The CP is a good derivative. It's a derivative, dH dt. So that's the beauty of equation 16. And the beauty of enthalpy, we said in an earlier class that enthalpy is correlated with heat. It's the closest thing you can get to having heat, something related to heat that's a state variable. And it's an exact differential. So look at that, that's beautiful. That the specific heat at constant pressure is the derivative of the enthalpy with respect to temperature. And look at this, compare this with the C sub V. That was, if we go and do a similar equation here with constant V, we already had a class on this and have talked about this. This is simply du dt, and we have seen that in this class too. So this is a nice comparison that for the constant volume, specific heat at constant volume, take the derivative of the energy per unit mass, because this little c means specific heat means assume it's divided by the mass. It's per unit mass. So specific heat at constant volume is the derivative of the energy per unit mass with respect to the temperature. And then the specific heat at constant pressure is equal to the derivative of the enthalpy with respect to T, temperature. And in this whole process, let's just emphasize this equation and consider that as a bonus equation. We also have the relationship that the specific heat at constant pressure is equal to the specific heat at constant volume plus R. Isn't that neat? Very, very nice. All right, that concludes our class H on the specific heat at constant pressure.